Good morning and welcome to our pre-lab video for our week 4 lab in Chem 105 here about the introduction to spectrophotometry. So this particular concept that we're going to be going after today is a relatively simple one. It's something called Beer's Law. Now Beer's Law is based upon this idea that when we do spectrophotometry, we're really looking at something in particular. And that thing that we are looking at is we are taking light, passing it through a prism, and moving that light in through a wavelength selector so that one particular wavelength gets shot through our sample. And what we are testing is how much light was there before the sample and how much light is there after the sample. And so based upon that, we can say, okay, we know how much was there before, we know how much is there after. The difference between the two is how much that the solution absorbed. And so the spectrophotometer can analyze that, and it gives us a display that tells us how much light is absorbed. Now, there's another form of this called transmittance, and it's basically the opposite of absorbance. What transmittance is how much light actually passed through. And so if we look at these two measurements, the amount of light that was present initially compared to the amount of light that went through, the ratio of those two, IT over IO, would give us that transmittance. And if we multiply that transmittance by 100%, we would get what is called percent transmittance. And that's one way that our data can be given to us by the spectrophotometer. Although more often than not, what we'll end up doing is we'll end up just measuring the absorbance directly. Now there is a relationship between the two. Absorbance and transmittance have a logarithmic relationship. The absorbance of a sample is equal to the opposite of the logarithm, that is log base 10, that'd be the log key on your calculator, of the transmittance. And so if no light is absorbed, that means that we have 100% transmittance. 100% transmittance would be a transmittance of 1.00, and the log of 1 is 0, which means that no light was absorbed. Now, our spectrophotometers are of this kind. This is called a Hawk spectrophotometer. And what we're going to be able to do is measure the relationship using the Hawk spectrophotometer between the absorbance of our light and the concentration of the substance that we pass the light through. That's what Beer's Law is all about. So Beer's Law sets up for us an equation. Absorbance is equal to K, which is something that we call the molar absorptivity. And that is something that varies from substance to substance to substance, multiplied by B, which is the path length, the distance that the light travels in the sample, and that's usually 1 centimeter, and C, the concentration. Now, if we take all of those things into consideration, the molar absorptivity is not going to change because we are going to analyze the same sample every time. And the molar absorptivity is specific to a given molecule. So in this case, we are going to be looking at potassium permanganate, KMnO4, and the molar absorptivity of that substance is not going to change. And furthermore, the path length is not going to change. We're using the same instrument, using the same cuvettes each time. The path length is a constant value as well. So we often see this kind of simplified into absorbance is equal to some sort of constant value. Let's just use epsilon, for example, here, multiplied by the concentration C. And since that value epsilon, that's going to be equal to the path length and the molar absorptivity multiplied by each other. Now, this particular relationship is pretty interesting because what we can ultimately do is we can create what is called a calibration curve, where we make a bunch of different solutions of different concentrations. And since the relationship between them should be relatively linear, again, think about this in terms of a y is equal to mx plus b. Our m would be the molar absorptivity, our x would be the concentration, and b should be roughly 0 here because, again, if there's no substance there, it shouldn't absorb any light. So from that standpoint, if we make a bunch of solutions of different concentrations, find all their absorbances, what we can create is a calibration curve where we put concentration on one axis, our x term, and absorbance on our y axis. And the results that we get should be relatively linear, where we can plot a scatter line, a scatter plot, and a trend line to tell us the exact relationship between the two variables. And that's ultimately what we're going to be doing in that lab. So we are going to be making these different concentration solutions out of the same stock solution. Now, the stock solution that we are going to be using is about 0.225 grams of potassium permanganate per liter of solution. And then we're going to use varying amounts of that stock solution diluted up to a benchmark. And so this equation right here, our dilution equation, is going to tell us what our new concentration is as we go through the process. So for example, if I have our initial concentration, C1 is 0.225 grams per liter, and I'm going to use 3 milliliters of it, the second concentration is going to be based upon how much I dilute that 3 milliliters. So let's say that I just dilute it to 50 milliliters, for example. Well, solving out my algebra here, I divide each side by 50 milliliters. And on the right-hand side, everything cancels. On the left-hand side, the milliliters cancel. The remaining terms, I just need to figure out what the concentrations actually are. And so you pull out your calculator here. And 0.225 multiplied by 3 and divided by 50 would give us a concentration of 0.0135 grams per liter as our second concentration. So I can take that, find the absorbance, and that would be one of the data points on my scatter plot. So looking ahead to your pre-lab here, you can see that the majority of the questions we've already kind of answered. Qualitatively, the relationship between absorbance and transmittance, we've talked about that. That's up in the previous materials. What is the, if I have a solution with a transmittance of 35.6, what is the absorbance? Well, remember that absorbance is equal to the log of the transmittance. So if I put in that percent value there, I should be able to find my absorbance just as easily. Oh, my apologies. It is the opposite of the log of the transmittance, and the transmittance needs to be converted to decimal form. And so I take the log of 0.356, take the opposite, so turn the negative into a positive, I get my absorbance there. And then this dilution equation is ultimately how you will solve for number 3. So this relatively short video will fill in more of the blanks about how to use the instruments and how to make those calibration curves when you come to lab this week. But this should at least give you a good jump start on doing the pre-lab. And remember, the pre-lab needs to be uploaded to Gradescope by Monday night. So make sure that you don't miss that opportunity. Have a good day.